Okay, this may be our last section of Chem 1402 material to talk about, but it's pretty neat. Well, let's introduce it first. It's neat because, man, look at it. We're worried about the greenhouse effect, right? And you want to plug stuff into the wall, and you want your electricity, but you don't want to destroy the environment doing it. So that's, in that sense, it's kind of good, right? This nuclear power. But there's usually a bad, right? And the bad is, what do you do with all this nuclear waste? And it's just piling up and piling up. And I'm not sure if you know about this, but there's a lot of politics involved. Yucca Mountain, man, our government has spent billions of dollars digging these deep holes into Yucca Mountain. But well, I guess if you lived in that state, you wouldn't want it either. So that's kind of where now it's just piling up around all the nuclear power plants. And I'm not sure what we're going to end up doing with all this stuff. Okay. But radioactivity I think it's pretty interesting. This it's called Fiestaware. Came out in the 60s, I think. And people were buying it, and it seems really nice and wonderful, right? But okay, now what's this little clicking noise? You've seen this in the movies. This is a what counter? Geiger counter, right? It detects what? Radioactive particles, right? So you can go around and walk around and see who's radioactive. There's background radiation, right? But more than likely, the beeps you hear is just from the detector, false positives. But yeah, this stuff isn't good, right? So what can block radioactivity? Can aluminum foil block radioactivity? What do you think, Jose? How about 2 hunks of aluminum foil? Steph? Oh, it's going to take a lot more than that. 3 hunks? All right. Now, if you are a fan of Superman, you know what I can use to block radioactivity. That's what kills him. Right? He had a science friend. And remember, he's Superman. So he made a suit out of this stuff, even though it was super, super heavy. What was it? It was lead, Kenneth. There's Kenneth. I knew it. Okay, now lead is poisonous, right? I don't want to have to end up washing my hands after I touch it, so I'm going to pull some out. And lead, you can bend it and everything, right? Lead bends and stuff. It's kind of nice. Okay. So, easily, right? There's maybe a little background, but. So make a suit out of lead. Kryptonite didn't bother Superman. Okay. So radioactivity. Since this is chemistry, we want to describe the chemistry of it. That means we have to know little particle names. We need to know how to write the reactions. But I think you're going to really like this because once you learn the rules of the game, it's really pretty straightforward. First, we have to know how to write these nuclide symbols. Okay? It goes like this. You have to write the element symbol. The mass number is a superscript, and the atomic number is a subscript. Now, let's see if Enrique can help us out here. Where are all these element symbols found? Periodic table. There they all are. There's all of our element symbols. All right? Where do we find the atomic number body? On the periodic table. And on this periodic table, all the atomic numbers, Kenneth, are what?
They're the protons.
They're the number of protons. What color are they? What's the color of the numbers? Blue, right? So you find, I don't know, potassium. It has 19 protons, right? So you'd write a little 19 for the atomic number as a subscript. Okay, if you're going to write the atomic symbol of potassium, you would write K with a 19. Okay. Then you have to write the mass number. Megan, what's a mass number? Number of... No, that's the molar mass. Does anybody know? Number of protons and neutrons. So how many? I don't know. You'd have to. I don't know. There's usually like double the number, so that's like 38 or so. I'm just going to guess at that one, right? But see how this nuclide symbols are redundant, and this is something in chemistry that you really don't see hardly ever. Once you give a piece of information, why say it again? What's redundant in this symbol? What did you say twice? The atomic number and the, well, the atomic number is the number of protons, but the atomic number and the symbol. Because if it's K, it has to be 19. If it's 19, it has to be K, so it's a redundant symbol. So it's really ridiculous to even have this number down there, but that's the convention. So that's what we're going to do, okay? So is every atom, so that's actually an atom of potassium. Is every atom of potassium have the same mass? They all have the exact same number of protons. Wouldn't they all have the exact same mass? No, because of the number of neutrons, right? Some are a little bit heavier than others. So some in the nucleus they have some neutrons, okay? So therefore we have nuclide symbols. And that is what makes stuff radioactive. Is simply not having enough neutrons or having too many neutrons. Even though it's potassium, you can make it radioactive. Just mess up the number of neutrons in the nucleus, and it's then it becomes a radioactive atom of potassium. Make sense? So write the nuclide symbol for a carbon-13 nuclide. We didn't really go into the naming. How would you name this nuclide? Potassium 38. Oh, I forgot. Sorry. Potassium 38. Okay, so we'll go ahead and write the nuclide symbol for carbon-13. You can use your cell phone to see your paper, I guess. Okay, so Cameron, what did you write? What did you write? Andrea, what did you write? Big C. The atomic number is, yeah, dang, I can't. 6, good. 6, and then what's on top? 13, which is exactly right. Hopefully that's what you wrote. See, it's not so bad. So in order for us to write these reactions, let's say we have a radioactive element somewhere. We want to show how it's going to decay into something stable, right? They're going to go through these decay processes and keep decaying until they become neutral. Oh, sorry, keep decaying until they become non-radioactive, right? So, and what are they going to do? They're going to emit or react with certain little radioactive particles. So we need to know the little particle names and formulas, and that's really rule 1 of the game to play this. You have to know the names and formulas of all these things. So, because the book could say a helium-4 nuclide is given off by this radioactive atom. Well, what is it? What's the formula for it? Does anybody know? So you need to know that. You need to know that a helium-4 nuclide is written that way. And then the name is what the book is going to say. So they might say helium-4 nuclide, but more than likely they're going to say, starts with an A what particle? What did that say, Connor? Alpha. Alpha particle. Okay. An electron. How do you write the symbol for an electron? They're going to use little e, superscript 0, a -1 as a subscript. And particle name, what is the homework? the questions, the book, what do they call this? Well, they might call it an electron, but the more common name is a beta particle. Beta particle. So beta particle is an electron. Alpha particle is a helium-4 nuclide. Very high energy light. They're going to call this gamma rays. And that's kind of a hint for what the symbol is going to be. If you're into the Greek system here, draw a gamma symbol. And then subscript and superscript are both just zeros. Okay. Sometimes you're going to have a positively charged electron emitted from this radioactive substance in its pathway to becoming non-radioactive. There'll be an E with a 0, and the subscript, can you guess? It's just going to be not -1, but +1. And their name for that, they're never going to say positively charged electron. They're going to say positron. Very good. Positron. Neutron. The book and the homework is going to call it a neutron. So I put that name in there. But the little symbol you have to know. All right. And the subscript and superscript makes sense because remember the subscript needs to be the number of protons. Well, it's a neutron, so there's a 0 there. And then the mass number is always protons plus neutrons. So if there's 1 neutron, it makes sense that it's a 1. Okay. Gamma particle, recognize how, right? The subscript and superscript are both 0. It's just energy, just giving off energy. Okay. So to me, this is rule number 1 in doing the homework. Know this table. That's half the battle. Here's the other half of the battle in doing the homework. In a nuclear reaction, you know it's going to be balanced when the sum of the subscripts and the superscripts are the same on both sides. So see if you can finish that reaction. A fluorine 18 nuclide is decaying. It's giving off a positron. Well, what's left? Right, the nuclide symbol of what's left. The only hint I can give you is subscripts and superscripts have to attribute the same on both sides. So Kendall, what did you write as the mystery nuclide?
18 on top and 8 on the bottom.
18 on top, 8 on the bottom. Yeah. Oh, man, you think I'd have that periodic table memorized by now? Perfect. All right. So you guys should be loving this, right? What a way to wrap up your last discussion on Gen Chem. So why does radioactivity occur in the first place? It says that the book tells us that a nucleus is radioactive or stable. It just depends on the ratio of protons to, what would you guess, Alyssa? In the nucleus. Protons to, I guess the only hint is nucleus. What's in the nucleus? Not electrons, but neutrons. Okay. That's what's going to make it stable or unstable if you mess up that ratio. So to predict whether something's going to be stable or not, you use the belt of stability, right? And in your book, in your handout there, it looks a lot nicer than up here. The screen's really dim. But pretty much if you're inside these little dots here, you're going to be stable, okay? And all they did with this red line, n equals z, They're just saying that the number of protons equals the atomic number. That's all. That plot, this red line really doesn't mean anything. I wish it wasn't even there. It just kind of confuses things. So what you're looking for are really these red dots. You see them? All these red dots in here. This is what you're interested in. I want to erase them so I don't. But that's the belt of stability. Okay? Even this blue cloudy thing doesn't really make a whole lot of sense. It's just those red dots is the belt of stability. You need to have that ratio in order to be stable. And if your ratio comes out to be above it, if you have too many neutrons, it looks like you have beta emission, a beta particle. Electrons are getting kicked out of there. If you don't have enough protons, if you don't have enough neutrons, right, you're below the belt of stability, you get electron capture or positron emission. Okay. Electron capture means what? That means that electron must be a reactant or a product by the hint of the name. This electron capture. In order to get into the belt of stability, you undergo this process, electron capture. The nucleus actually captures an electron. So the electron must be a reactant, right? So you just have to recognize that because you're going to have to put the electron on the reactant side to recognize that. Or you could go and undergo positron emission. If you're below the belt of stability, this radioactive particle could undergo positron emission. So from the table, you know what a positron is, but if it's emitted, this positron must be on the what side? Product side. Okay, so it's not so bad. Let's see if we can practice reading this table a little bit. A nucleus, Audrey, a nucleus with 20 protons requires about how many neutrons in the nucleus to be stable? About 20, right? Because you want to get it in the red region there. 20. Completely agree. And a nucleus with about 80 protons, Andrea, requires about how many neutrons?
We're trying to get into the red dots, right?
Yeah, you want to get to the red dots. Yeah, I would say around 120. I agree with that, right? You just go straight up from 80. You hit around 120 somewhere, right? Somewhere around there, right? Okay. Now, no atom with more than blank protons in its nucleus can be stable. Mia, what would you say? No atom with more than blank protons can be stable. Pretty much, where do all the red dots end? Where does the belt end? You see it? Pretty much right here. And go straight down. You'd end up with around, what would you guess that number is? 85, 83, 84, it'd be somewhere around there. If you really zoom up on the plot, the actual answer is 83. Okay. So that's how we read the belt of stability. Don't have to memorize it, just know how to use it. Common nuclear decay reactions. Okay, so this is what's going to be happening. These are the reactions that we need to handle. Alpha emission. So an alpha, you have to put an alpha particle on the product side because it's being emitted, right? Beta emission. Know what a beta particle is. Make sure it's a product because it's being emitted. Positron emission. Know what a positron is. Put it on the product side. Gamma emission. Make sure you know how to write a gamma symbol. Put it on the product side. So emission just means product side, right? Electron capture. That's the only one that's on the reactant side. Okay. So go ahead and see if you can do this. Cobalt-60 undergoes each of these types of decay. Fill it in. If cobalt-60 is undergoing that decay, Jose, just to get you started here, cobalt-60 had better be on what side of the reaction here? Should be on the reactant or product side. On the, yeah, the reactant side. So make sure you have your cobalt-60 nuclide as a reactant. And see if you can fill this in. Okay, Steph, what did you write for the alpha emission? Yeah, give it its name. Cobalt-60? Oh no, I mean the name of your answer. Mn is manganese. Manganese 25 or 56? Which is manganese 56. Does everybody agree? Okay. What's manganese? Manganese is 25. Oh, I could have done the math and done it myself. Okay, how about beta emission? Connor, answer. Nickel 60. That means this has to be a 26. Well, whoop, a 28, right? No. Yeah, 28, because 28 and negative 1 is 27. Enrique, positron emission. Answer.
66
How do you name it? You have to name the nuclide. It's always the name first. Iron 60. Iron 60 looks like that. This guy's got to be a 26. Bowdy, gamma emission.
It's still cobalt-60.
Cobalt-60. Just less energy is all. Last one, electron capture, Kenneth.
Iron 60.
Iron 60. This has to be a 28. Something seems messed up here. How many protons does iron have?
You wrote 28, it's actually 26.
Iron has 26 protons. What has 28 protons?
Well, 27 plus a negative 1 is 26.
Oh, it's on the reactant side. You're right. I didn't even see that. Right, it's over here. You're right. Thank you, Megan. Okay. It's not so bad, right? So let's just see if you can knock these out. And then we can call it a day. So if you can do these, you can do anything that the homework's going to throw at you. Just make sure you get the same answers as those around you, and we'll be good shape. Yep. Well, it can't be Cu, right? Because Cu is copper. What are the possibilities here? It can't be Cs, not cesium. Wow. Keep looking up here. It might be this. Just Google it. You have your phone? I think that's the only choice you have. Cm looks like the only choice you have, isn't it? Because Cr is chromium. Curium doesn't have an E in it.
Oh, that's the most random of it. It's the only one we haven't used. Yep.
You guys that asked for a letter, I'm pretty sure, I think it's in your folder. Connor, I think it's in your folder.
Okay.
I think so. Kenneth, I think your letter's in the folder. Because I had them, I think that's where it's at. It's not in there?
No.
Shoot. Connor, see if yours is in there. Pull it, here it is. I didn't get it put in there. Yep.
Are you gonna give us these on the?
No, that's why you have to know it.
I just asked so I know to know it.
What is scandium? Scandium, I think it's SC, isn't it? Scandium?
Oh, yeah, because SN is 10.
Yeah, SN's 10. Yeah, SC. I think SC is scandium. Now, you can Google now.
There's no curium is CM. Just off the top.
Well, now you know. They're pretty easy to figure out, though. I mean, you don't have very many
But if
choices.
you do it wrong in the whole thing.
Well, no, you can't really do it wrong because you know that Ca is calcium, Cu is copper. Your only choice up there is Cm.
Well, I don't know what PT is.
You think that's going to be curium?
No, but I'm saying.
It's going to have a C and a. No, they're all that way. You'll have to figure them out.
Atomic number 96. It's one of the white ones. I would have never seen it.
Alright, next to this. So on that quiz that we just took.
Mm-hmm.
Oh, never mind. I won't be able to find it.
Just go get it.
I can go
You
get
have
it?
10 minutes.
Alright. Explain it to me.
Dig yours out of there.
Alright.
You did. Everyone else got 0.75. Yeah. So you got. So make sure AG plus goes to AG solid. So that's 0.8. You ended up with 0.94. P0 solid. Everyone else getting. Where's someone who got 0.75? A lot of people did 0.75. I thought I saw a lot of points. Here's one. 0.94. Okay, that part looks right. Okay, 0.94, 0.98, all over 2, log of 0.25, all over. Well, it's 0.025. That's where you messed up. Ah, you had it all right.
Oh, we did all of them. Go by. I was gonna wait in case you said something.
Say something important after the meeting.
Well, you can go over your quiz that you just turned in. You have questions on that? Okay, I think this is a good exam question because you're going to have to try to figure it out because you weren't asked to know the names of everything, right? So you know it's going to have to start with a C, and then it's going to be some other little subscript letter. And your choices, CO doesn't make sense. Okay, then there's CR, but CR you're supposed to know its name, and that's chromium. And CS, I think you're supposed. S isn't in the word, so it can't be CS. CS is cesium. It's going to have to be CM. CM is down here at number 96. It can't be CF because there's no F in cerium. Okay. Oh, that would be a. That's. Oh, there's no E. Okay. Yeah, it's curium. So there's no E.
It says curium bombarding with alpha, so alpha is.
Alpha is a 4 down there and a 2, isn't it? No, 2, 4. You're right, 2, 4. That should be a 4 up there.
Yeah, I was just trying to figure it out.
The curium was synthesized, so you have to make. You're right. You have to make this.
Yeah.
The product with curium-242 and a neutron.
A neutron. So is that right?
So you have to figure out what this guy is.
But
So this has to be a
right?
neutron. Yep.
1 and 0.
You got to figure out what this guy is. What are you slamming into?
42 and 1 is 243 minus
So
4,
243 has to be up there.
239.
Yep. There you go.
And then 96. 94.
Yep.
PE.
There you go. All right. Well, have a good day.